many cases, we can then do that multiplication for either free or for very cheap. All right. Well, we are just moving right through everything I thought we might talk about tonight. I think the person who submitted a question still is not here, so I actually had some follow-up questions for them on this front, although maybe we can talk about this briefly and always come back to it later. The question that was posed was kind of more of a general statement, a general curiosity about reader-writer synchronization patterns when you have multiple readers or multiple writers. And there's a kind of a multitude of different questions that can be asked on this front. And the first questions either you would have or information that you'd be given is, what are you reading and writing into? Are you reading and writing into a circular buffer? Are you reading or writing into a linked list of unrelated objects? Is it an array of fixed size objects? Are we looking at a stack or looking at a FIFO? There's a lot of information that you want to gather when you start figuring out what it is that you're trying to do here. And then the second thing we want to do at a very high level is figure out, are we going to come up with or try and come up with a lockless solution or a solution that does involve involve mutexes? So, and by not involving locks, usually we would use some sort of atomic operations to atomically insert or atomically remove entries from our list of pending tasks. And as you're probably aware, there's some pros and cons of using locks versus atomics. Atomics obviously avoid some of the overhead of using locks. You don't have system calls. You don't stop the thread, which kind of has the overhead of a context switch and all of the other stuff that goes into a context switch. But the downside to atomics is, well, sometimes they're not possible if the system doesn't have atomic support. Sometimes if you have a single threaded core that doesn't have thread preemption, your atomic solution could have some odd behavior and might not be possible to do at all if you're expecting two threads to potentially contend to something, and if the threads have a contention such that one is waiting on the other one, but the other one never gets time to run, you might end up getting stuck indefinitely. And not to mention, if you have some more complicated data structures that you're trying to synchronize, it might not necessarily be impossible to use atomics, but it might become very difficult to use atomics. I think, and obviously the kind of the beauty of using a mutex, using locks, is that it is very simple to implement something like that in the context of an interview and be fairly confident that you're doing it correctly. That's kind of my number one concern about trying to write something that's lockless using atomics in an interview context, is it's something that, at least for me, not it being something that I don't do every single day, kind of requires some strong consideration and thought to make sure I've done things correctly, versus using mutex to just say, okay, I want to write something into my list. Okay, well, first I acquire this lock, then I do my operation, and then I unlock it. I can be fairly confident that I'm not introducing some possible race condition. And as long as my lock and unlock are pretty straightforward, I can also be reasonably confident I don't have any sort of deadlock or any other sort of possible corruption. So these are all the sorts of questions that one might ask or try and inquire about when you're given a sort of task like this. Is what are the goals or objectives, and then trying to figure out what are the best tools to meet those goals or objectives. For instance, if your job is to implement a FIFO, then using something like a circular buffer, it might be the easiest way of going about doing it. Because then all you have, once again, is your read pointer and your write pointer. And even if you have multiple entities reading or writing from it, it's still fairly easy to implement a lock-based solution and relatively easy to implement a lockless solution. The more values you're trying to keep keep synchronous, keep consistent, the more difficult it is to use something like atomics. Because once again, atomic only allows you to change one variable at a time. or one object at a time, and trying to change. If your data structures involve multiple variables to keep track of the consistency, it ends up becoming a very difficult thing to do. For instance, if you have a doubly linked list, you have both a next and a previous pointer, it becomes difficult to atomically update both of those in a single operation. Not that it's impossible, it becomes more difficult. You know what, Mufidal, not to put you on the spot, but did you have any areas that you were hoping to explore on this topic further?
Actually, yeah, I guess, yeah, I think I get the gist of the synchronization if it's one reader and one writer. I mean, I think trying to wrap my head around, even though I've used this is the first time I guess I've conceptualized this. So, what's the difference between a producer consumer pattern versus a reader writer pattern? And then, how would I do if there are multiple readers or multiple writers? I think that's kind of what I was trying to understand based on the material so far, and kind of, I think needed some clarification.
Yeah, absolutely. So having a single reader and a single writer makes things in some ways simpler. But having multiple readers or multiple writers doesn't necessarily make anything more complicated, as long as you're able to kind of well define what a task is. So whatever it is that you're reading and writing to and from, you have to make sure that it's a self-contained object that doesn't leave behind stragglers once you update something. So let's say we have, just for the sake of argument, a circular cube. We're implementing some sort of FIFO sort of thing, and let's say we have multiple readers and multiple writers. So we might as well make it more complicated. At any point in time, we're going to have a write pointer. In other words, where should the next write occur at? And we would have somewhere behind it a read pointer. At the person who's reading this, where should they read from next? And using a circular buffer, usually you'd have some sort of data structure that involves containing the length of that entry first. So you might have size and then your data. So each entry in this FIFO, each entry in this circular buffer is one of these structures. Or at the very least, each entry has the same size field first. So if we were implementing something using locks, then in order to write something, and let's just assume we have a single global lock, the circular buffer lock, and doing this kind of in terms of pseudocode, first we would need to lock that global lock. Then we would need to do some sort of mem copy to the right location from our whatever temporary buffer the data was coming from. Then we need to update write pointer, call it the write pointer, and then we need to unlock. And then if some other writer tried to write at the exact same time, they would get blocked at the lock. And once the previous write had completed, they would be able to lock and then add their entry next. Obviously, there's a couple edge conditions we would need to check. We need to make sure we don't write past the read pointer. So we would presumably need to have here some sort of check to if write pointer plus size is greater than read pointer, error, or whatever it is however it is you want to handle the case of running out of memory. Maybe you return an error, maybe you assert. But at a high level, this is all you would need to do. And then from the read perspective, it ends up being quite similar. The reader would lock the FIFO, would confirm that there is something to read on it, and then mem copy it out and update that read pointer. There's the question of how do you signal the reader that there is something to read? And there's obviously multiple ways we could go about doing that. One simple one might be using something like a semaphore. If you have multiple reader threads who are just kind of waiting around, have them all wait on a singular semaphore before doing that read. What you could also potentially do is, if you were less concerned about threads just waiting around doing nothing useful, is have those threads in like a busy loop where they essentially do this in a busy loop, which obviously is more wasteful, but just wanted to give us another example. Lots of different ways of synchronizing the notification that there is something to read. That ends up kind of being a separate problem. Like, there's a problem of how do you make sure that the data that you're sharing is consistent, and then there's the problem of how exactly do you want to indicate to the other side that there is something to read. From a hardware perspective, maybe you have something like an interrupt that the other side then gets notified of when there's new data to be read. So from a mutex or a lock-based solution, it should be roughly this simple to have something like a circular buffer FIFO style. There's one more potential complication I want to bring up. As I mentioned, I keep using the word FIFO, and the problem with this is that or at least it strongly implies that there's supposed to be an ordering to the data. So what happens if, for instance, a reader was running and acquired the lock, and for whatever reason was holding the lock, when two writers both wanted to come in one after the other and write something? If there is a true ordering to the data that needs to be written, we would need to make sure that the first person who called write, the first person who's waiting on this lock, is the one who gets the lock first, who gets to put their data in there first. But using just a simple lock mechanism like this, if multiple writers happen to be waiting on this lock while a single reader, or maybe the previous writer, was doing this operation, because memcopy could take a while if you were copying a lot of data. If you have multiple writers lining up, they then might start writing to the circular queue out of temporal order. Like, they might be writing data out of the order that the data was originally collected or intended to be in. So that's kind of another potential complication on both the read side and the write side. And it ends up being a very difficult problem to solve, because if there are truly let's say multiple readers, even if you retrieve the data from the FIFO in the correct order, and there's multiple threads for each one of these readers, there's no guarantee that the OS is going to schedule those threads such that the first reader gets to run first. So to say that again, even if we solve
I understand that. I think that part is clear. Glenn, that part is clear. So that's exactly why I guess I'm asking the question.
Sure.
Or is my question not valid at all? I guess you can still, say that, I guess, too.
Well, no. Maybe you can state your question again, if you don't mind.
So I guess just take this example. You have one writer and you have multiple readers.
Yep.
And there were two examples that were given. I think one is this turnstile approach, and the other is the light bulb approach. And as you mentioned, I think neither of them maintain precedence, or as temporal order. So that's definitely there. But I think I think so. That's kind of what I'm maybe first is, okay, how do I how are those being implemented in here, and is if they're writing the way they were described in the example, it wasn't the pointer of a FIFO, it was called the buffer, and the buffer itself gets locked. So if someone is reading from the buffer is locked, and vice versa. If someone is writing to the buffer, it's the same. So I think that's what is not clear. How if it's let's say just one writer, multiple readers, and if you do end up after a write there's a subsequent write, then it just waits for all the readers to finish before it can even write.
Well, those are kind of, yeah, there's two options there. One is, as I kind of have here, there's a kind of a global lock, whatever the object it is that you're locking, wherever the data is that where it's being stored, a global lock such that a reader and a writer can't operate at the same time, which obviously is kind of the easiest and safest approach from that perspective. Because then you never have to worry about well, really, it's very brute force course sort of synchronization. The other approach would be to say that a writer is allowed to write at the same time someone is reading, because logically speaking, as long as you're not overwriting something that already existed, someone should be able to read something at the same time you're writing because they're occurring at different locations in the buffer. So from that perspective, there isn't a need to have a global lock protecting it. And you could either use locks or start using atomics to start solving this problem. So let's see, let's move things a little bit here. So let's assume, once again, we still have our read pointer and our write pointer. And maybe for the sake of argument, we can just say that it's a straight arrow. We have our write pointer and we have our read pointer. And we can ignore the fact that these oftentimes are implemented as a circular loop. What our writer can do is just write. Whenever a single writer, he can write whenever he wants, because there's this space is all available to him. He can just, whenever he wants, write data. And when he's done writing that data, he needs to update his write pointer to be wherever the new tip of the code or tip of the data is. So the writing guy can just keep writing indefinitely. The reading guy is kind of where it gets more interesting, because the reading guy only can read up until the write pointer. It can only read this section. And the reader relies on the write pointer to always be valid. Like the write pointer can't sometimes point back here or sometimes point way over here. The write pointer always needs to point at a valid location in memory, such that everything prior to it had valid data copied into it. So this write pointer needs to be a valid value, a reasonable value, whenever the reader needs to access it. And you could, once again, have a write pointer with a lock around it, and you lock and unlock accordingly. But because this ends up being such a simple object, I mean, a write pointer is just logically an integer, what we can do is instead just atomically write to our write pointer. So such that the writer will write data and then atomically update write pointer. The reader simply needs to atomically read the write pointer, and if and only if there's space in between the read and the write pointer, then read/process that data, and then presumably repeat. So we are having a single write pointer that is atomically updated and atomically read. This obviously solves the problem of a single writer and a single reader. if we have multiple readers, which I think is what you mentioned earlier, we now also need to make sure that we have a valid, well, that the read pointer ends up being valid as well. Because we only want a single entity to be reading a particular section at a time. So if we have, so let's say this is the one reader solution. If we have a 2+ reader solution, what we need to do is still, once again, atomically read the right pointer. Then what we need to do is atomically update the read pointer. Not that we've read it yet, but the reader needs to essentially claim or reserve or ensure that no one else is going to read that data. And the only way to ensure no one else is going to read the data is to move the read pointer forward such that the other readers don't even realize that there was data to have read. So atomically read the right pointer, and I guess once again, check, well, right here, check right pointer is greater than read pointer. And then, well, process data. When I say atomically update over here, for this single writer and single reader case with regards to the right pointer, I literally mean that using an atomic store and an atomic load, such that any time someone calls load, you get a valid value. That's what I mean in this case. For the case on the left side, we need to atomically update the read pointer. Not only do we need to make sure that the value gets updated, we need to make sure that no one else at the same time tried to read it as well. Once again, there's multiple readers, they might all be trying to read data the moment the right pointer is updated. So they might all see, oh, look, there's data to read. We're all going to try and jump on it at the same time. So by atomic read, rather than doing a store, what we instead need to do is something along the lines of a compare and swap. So what we want this to be is we only want to update the read pointer if no one else has yet updated the read pointer. And if someone else has snuck in and updated the read pointer ahead of us, then we want to potentially bail out. And compare and swap, there's a couple others as well, but compare and swap is going to be the typical tool. You do that because you're going to compare that the current read pointer, at least the read pointer value that you thought it was, is in fact what the read pointer was at the time this atomic operation is performed. And then only if the compare succeeds do you swap or do you update the read pointer to the new value. So this whole operation, those two tasks need to be done atomically as a single operation. And fortunately, many systems provide such an atomic operation. So to summarize this, if a single writer and single reader, we really only need to worry about having an atomic or locked right pointer. If we have multiple readers, then we also need to keep track and make sure that the read pointer is updated and maintained atomically as well. Was that helpful? Was that kind of what you were looking for?
Yeah, I think that helps because this being able to reference a read pointer, which is, I mean, I think it's a different way than I guess what we had discussed previously in the other lecture. So I think that does make sense. And I guess the same would apply if you had multiple writers and one reader as well. I think it's the same idea.
Definitely the same idea. Obviously, with multiple writers, so with a single writer, that writer can just write data whenever it is that they want, and they just write it at the right pointer, and it doesn't matter. But if you have multiple writers, the writer essentially needs to reserve memory, reserve space on the buffer or the file or whatever it is, needs to reserve space prior to writing. So what you would have in that case is not just a single write pointer. You would have a well, you'd have two write pointers, a write one and write two, and you would need to atomically update this second write pointer to kind of reserve the memory to make sure no one else tries to do so at the same time. Sorry, let me take that back, actually. Using two write pointers is one approach. The second approach is just to update the write pointer. There's two problems we need to solve here. One is we need to make sure that we reserve memory so that no other writer tries to write to that particular space while you're trying to write to it. While at the same time, we need to make sure that the readers don't try and read past anything that has been written to yet. So the readers still need to have a notion of a write pointer, which is up until this point is full of valid data. But then from the write pointers, the writer's perspective, they need to know at what point can I start writing data, which might be different than the reader's notion of where data has been written to. So similar problem, similar solution, can be solved with atomics, and yeah, that's all she wrote. This once again is oftentimes a circular buffer in practice, because you usually can't just keep on going indefinitely in one direction forever. I mentioned, well, I didn't write it down. I mentioned at the beginning that what we're reading to or writing from ends up greatly affecting what our design implementation is going to be. So I think circular buffers end up being a very easy thing conceptually to talk about, because they don't involve very many state variables with regard that have to be kept synchronized with each other. If we have something like a linked list, then it becomes a bit more, well, it becomes potentially more difficult to add things to a list or remove things from a list in an atomic way. That is still possible, but you have to kind of look at it in a slightly different manner. So maybe that's why when you were reading up on things that talk about things different, was maybe there was maybe the underlying data structures were slightly different, which required a different approach. And I see there's a question: are there any approaches, ideas to allow temporal ordering for writers without using timestamps and sorting the data itself? There's a couple approaches. One approach is you can have a master thread. Actually, let's take a step back. Let's look at it more from the context of what we talked about here. With the locks that we talked about, if someone's holding a lock, then everyone else is just going to back up on it without being able to do anything about it. And during that period of time where the lock is blocking everyone else, multiple entities might be backing up, and then those writes might not end up occurring in the order that you intended. With the atomic approach that we've done, yes, we're atomically updating the write pointer, or even in the multiple writer case, we're atomically updating the write pointer to make sure that the value is always internally consistent. But we're not, for a kind of temporal data, we're not actually expecting for there to be contention. Like if you expect data to come in at time equals 1 and then again at time equals 2, the only real concern is whether or not the data at time equals 1 gets blocked such that it can't insert it until time equals 2 data comes available. And with atomics, we shouldn't have that scenario. We shouldn't have this scenario where someone is blocked and unable to write for an extended period of time, so that we shouldn't have there shouldn't be the effective concern of data being written out of order. So that's one way of kind of avoiding the problem entirely. In terms of other solutions, and this will it kind of becomes somewhat of an operating system problem, which is some operating systems, if you have one thread holding a lock and other threads trying to acquire that lock, some operating systems will well, many operating systems, frankly, will give the priority, they'll give the thread after the lock is released, will allow the thread to run that has the highest priority who's waiting on the lock. But if all of the readers or all of the writers in your question have the same priority, in some operating systems, those waiters are ordered by the order in which they started waiting. If that makes any sense. So that the thread who was waiting first and presumably has the oldest data will be the first one to get an opportunity to run once whoever it was who was holding that lock unlocks. So some operating systems work that way. Some of them don't. Many of them don't. Many operating systems, when someone releases a lock, doing some hand waving here, all of the threads that were waiting on that lock all get woken up at the same time, and then it's somewhat of a race to see who gets to acquire it first. And then there's other approaches that operating systems can take as well with regards to those locks. So for operating systems that do have that implementation and requirement that the locks are released, or threads are given the locks in the order in which they try to acquire them, then that also, frankly, handles your problem. And it might be possible in some systems, especially on an embedded system where you have a lot of control over the operating system, it might be possible for you to write your own wrapper, your own implementation, such that you get this ordered waiting, even if the operating system itself didn't provide ordered waiting. Happy to talk more, but there's at least a couple approaches, a couple different ideas we could go about to make sure that writes occurred in the correct order. You also mentioned without using timestamps, and well, I mean, you hit the nail on the head. Timestamps, or more importantly, some sort of sequence number, can also be used, and you could potentially do it such that you can write in any order you want, such that the sequences might be out of order in the buffer, but then on the reader's side, you could add some assurances that the readers that happen to get data that's out of order wait until the entity that has the next in sequence object to process gets a chance to process it. So I know you said without using timestamps or sequence numbers, but you don't have to have the data in the buffer be ordered. You could always have the ordering occur on the reading side.
Yeah, thanks, Glenn, for those insights.
And there's a lot of, I mentioned, I keep saying that for simple data structures, the implementation ends up being fairly simple. For complex data structures, the implementation ends up usually becoming more complex. But there's almost always a way to achieve your aims using atomics. It's just a matter of how complicated do you want your design to be. Trying to think of it. Maybe I'll give one example. I implemented at one point in the past a producer-consumer system. It was for a sensor sample, so Excel, gyro, magnetometers, those sorts of samples. And you had all these different sensors producing data potentially simultaneously. And I wanted the data to ultimately be read in the correct order. So in order to solve that problem, I used a couple of different approaches. One is I used separate buffers per data type. So there was a separate circular buffer for Excel versus gyro versus magnetometer and so on, so that at least for any particular sensor, the data was coming in the correct order. But you still have the problem of where is that memory going to come from? So a true circular buffer is typically going to be allocated in advance. So you would need to, in advance, allocate 3 buffers. And if the gyroscope was disabled, then that buffer would essentially be wasted. You wouldn't ever use that data. And in an embedded system where you have limited memory, obviously that's wasteful to have a bunch of memory allocated that isn't being used. What you'd ideally want to do in that case is to make the Excel and magnetometer circular buffer slightly larger. So another approach, rather than using it as a true circular buffer, what you could instead have is a linked list of samples, so that you have your Excel and your gyro and your MAANG samples. Each one has a head, and you have sample number 1, sample number 2, and so on for each ones of those. And then each one of these blocks is the same size. So MAANG and gyro sample are all the same size. So you could have some sort of heap that was just a big array of fixed size blocks. And then whenever you had a new Excel sample, you just essentially take one of those blocks and stick it on your linked list. And this is to avoid any sort of fragmentation issues as well. The problem with this design is that linked lists are fantastic, and they're also fantastic at wasting memory. Because even in the best case scenario, your linked list is going to have, let's say, 4 to 8 bytes just for the next pointer. If it's a doubly linked list, there goes another 4 bytes for the reverse pointer. And maybe there's some other state involved with your linked list in addition to the next pointers that also has to be maintained. And for, let's say, an Excel sample where you just have an X, Y, and Z, each of which might not even be 4 bytes each, but let's say you only have a 12 bytes in total sensor sample, wasting 4 bytes for the next pointer and increasing your sample size by 30% just to maintain this linked list ends up being more wasteful than having this buffer sitting not being used at all over here. So one potential solution to that is, rather than having it being a linked list of individual samples, it could instead be a linked list of a table of samples. Because you know that you're ultimately going to have more and more samples coming in, so you allocate enough space for 6 samples, let's say. And on sample number 4, all you need to do is stick it into the spot that you already had pre-allocated. And then when you get to 6, then you just allocate another set of 6 blocks. And you have the same thing with magnetometer and gyro as well. So rather than it being a linked list of samples, it is a linked list of, let's call it, arrays of samples. So now you have in kind of in a sense from before, we now have a read and write pointer for each table. Because it's possible that the entity reading has read samples 1 and 2, but hasn't yet read samples 3. Yet the writer is now over here writing sample number 7. So we can do all of this with atomics in such a way that we have no fragment or little fragmentation, low overhead for the linked list cost, and efficient use of memory if one of those sensors is not being enabled at that particular time. So we can do all of that, but as you can guess, now we have atomics per table, per sensor, and it becomes a bit more complicated. So I'm not necessarily going to go into detail of how you go about implementing that, but I just wanted to give an example of, depending on what your goal is, your data structures to achieve that goal are going to be potentially very different. And the synchronization requirements, or how you'd go about synchronizing those data structures, also varies. And that's why it's always worthwhile, and I was kind of off topic from the question of synchronization now, but it's always important when you're being asked to design or implement something, is to make sure you have a good understanding of what it is you're supposed to optimize for. Even if they say optimization isn't important, it probably is still worthwhile to do a little bit of optimization. But in general, if something doesn't need to be optimized, don't optimize it. Write code that is clear, concise, and hopefully easy to explain in the interview, as opposed to trying to overly optimize something that the interviewer didn't need you to optimize. And doing this when all that was needed was this, is it looks bad in a number of different ways. So optimize what needs to be optimized, don't optimize what doesn't need to be optimized. All right, I got a little bit off track there, but any other questions on this topic?
Glenn, a generic question. So if we are asked to, write test cases, if there are any bug in the code, and if we are asked to write test cases to find it in generic in a multi-threaded system, are there any patterns to go about? Or
so you're specifically, it's not that you're being asked to find the bug, you're being asked to write test code to try and create a bug or discover a bug that way.
Right. Yeah.
That's an interesting question. I don't know. Clearly, that's something that could be done. Normally, I see when we have this kind of find the bug problems. Normally, I see people like, "Hey, here's a bunch of code. You get to choose how it is you want to debug it, whether it be writing a test case or just reading through the code or doing whatever it is." But if the requirement was strictly to write a test case for it, I guess what I would want to do to test these sorts of potential problems is to try and see if I can get two things to occur at once. So if I had multiple readers and multiple writers, I would want to create a very large number of them. Or whatever the most number I can create is, I would want to create it, whether it be on an embedded system with only a single thread, maybe only create a couple of them. But on a more general purpose, high level operating system, maybe you're creating 100 or 200 readers to see if you can't kind of brute force reproduce a problem. Readers or writers, whatever it happens to be. Trying to think of what else would I do from a test perspective to catch one of these. If oftentimes, whether using atomics or not, these operations usually end up being very quick. I mean, yes, I said memcopy could be slow, but most of the time, whatever it is that you're doing, that insertion, that reading or the writing or the insertion or deletion of the data ends up being fairly quick. And because it's fairly quick, you could have something like a race condition, but never exercise that, never actually have that race condition occur because it just happens to be so quick that no two of them ever happen to do it at the same time, or at exactly the same time. So my next thing I'd want to do is try and make whatever it is slow. So if you had an implementation that was like this, then we would want to have some very large sizes. If we were doing something that involved whether it be a network or a file system or whatever it is we were writing to and from, if there was a way to slow that down, is a way to slow down the network, slow down the file system, slow down whatever it is that can be slowed down, such that you have a larger surface area where, in this case, that memcopy might be running. And then you're more likely to hit the case where two of them are doing it at the same time.
Okay. Yeah.
Oh, sure. Yeah. I'm trying to think if there's anything else that I would do on that front. Increase the surface area, increase the number of people trying to do it. And then I guess this kind of goes without saying for any sort of test cases. Are there any error conditions? Here I said if write pointer plus size is greater than read pointer. But what happens if it's equal to? Is there a possibility that there's some edge case where the equality or greater than equal to check is incorrect, and that results in a bug, which could be a synchronization bug or could just be a functional bug. So finding a way to force the write pointer to equal the read pointer, or forcing the write pointer to equal the same size as the read pointer. Or you also notice here, I didn't write any wraparound code. And in the circular buffer, it's going to wrap around eventually. So writing a test case that at least makes sure it wraps around once, and also test the cases where like the wraparound that is at well, the size of it is at exactly the wraparound point? Or what if you tried to enqueue something that was 3 times the size of the overall buffer? Those sorts of things would be test cases that in general I would want to check all those edge cases.
In case of circular buffer, Glenn, so how can we make sure, because it can overwrite, right? So comparing the write pointer to the read pointer, does it make sense? Because it can always be valid, right?
Yeah, you're right. You're right that the take the case here where, let's say this is 0. The read pointer is actually larger than the write pointer in an objective sense, because 0 is on this side is, let's say, 1,000 or 100 or something. The read pointer has technically a larger value, a larger address than the write pointer does. So your comparison can't be a greater than or equal to check can't be the only thing that you're checking for. All that you know is the read pointer is always behind the write pointer. So if you see that the read pointer is greater than the write pointer, that's okay, as long as this boundary is in between the two. So this check right here usually ends up being several statements, like if write pointer is greater than read pointer, then make sure this is the case. If read pointer is greater than write pointer, make sure this is the case, so on and so forth. So it ends up being a non-trivial sort of check to make sure that it's valid, which is why it's a potential place for errors, and you'd want to kind of force that check.
Okay. Usually, what is the approach taken then in case like if we are there are multiple writers, it is only writing and there is no reader. So should we block the next writer to override the previous value, or it's all application specific, whatever is the requirement is?
That ends up being an application specific thing. If you are trying to keep, for instance, a historical log of all the events that have occurred on your system, you want to keep all the events from the last 5 minutes. Then once an event is 5 minutes old, you want it to be overwritten, or what is potentially overwritten, with a newer event. Versus, let's say you're processing Excel samples and you don't want to drop Excel samples, that sort of thing. So in my experience on an embedded system, you design your link, you design your FIFO, you design your circular buffer implementation from the get-go with the understanding of whether or not you expect it to you write it from the get-go with the understanding of whether or not you expect it to be overwritten or not. So if, for instance, you have a system that you don't expect, your circular buffer to ever wrap around, such that the write pointer tries to write past the read pointer, then maybe you consider that to be and you add an assert in that case. Like you panic the system, because either it means that something is broken, like the reader is stuck or not running, or it means that you've incorrectly sized your buffer. In the case of systems where you don't want to drop samples, that's where it becomes a little like cases where you don't want to drop samples, you size it appropriately so you crash or you make the buffer bigger. In another case where you are okay with overwriting it, that's where it gets a little bit more complicated, because in my kind of design here, I said that the write pointer, or the writer, was only ever writing to the write pointers, and the reader was only ever writing to the read pointer. If you have a case where you do have wraparound and you want to overwrite the oldest data, then that means the writer needs to both update the write pointer and update the read pointer, because there's data that now essentially has been lost, so the read pointer needs to be updated to reflect the fact that there is no longer data there available to read. And it ends up being still a doable thing to implement, but it becomes far trickier to implement because you need to make sure, like for this implementate design down here, I said that a reader could update the read pointer and then subsequently process the data. But if the writer can update the read pointer and then overwrite that data, then this processed data might now not process the data that it was supposed to process. So this processed data or copy data out now needs to be up above somewhere to make sure that you have a valid copy of the data before updating the read pointer so that you can process the correct data. And then finally, you have the option of just saying, oh, well, the FIFO was full, so I'm just going to block the writing thread until space becomes available. And that's, well, potentially deadlock sort of inducing case, but also another possibility. All right. Well, if there aren't more questions on this topic, maybe I will once again open it up. Are there any other topics folks would like to cover or discuss? I have a couple other things prepared that I could go over, but before I do that, does anyone else have something that they would like to bring up?
I guess not to beat this one to death, but there were two patterns that were mentioned in the notes. The turnstile and the light switch, was it? Are those valid? Or, I think it sounds like your solution would work. So do we need to kind of pay attention to those, or, or is that kind of just make a mental note, but it's kind of independent?
I have to be honest, I don't know what you're referring to when you say light switch turnstile.
It's like I think it's described as a barrier pattern where, I think that's with a semaphore. You can hold a bunch of readers until all the readers are finished, kind of thing.
Yeah, I mean, unfortunately, for better or worse, I'm not aware, at least of those titles. Maybe I'm aware of what they do, but I haven't heard those particular terms before.
Got it. Okay, understood. That's fine.
Sorry about that. Was that from what was that? Module 4 from synchronization? Is that one of the topics there?
Yeah, I think it's concurrency and synchronization. It's part of that. Which is
so,
just the tricky one.
Honestly, I should probably read up on what those other guys have been teaching. Although at the moment I'm somewhat out of the loop on what they've been up to. So sorry to kind of not be able to answer your question. Fortunately, though, in a couple weeks, I forget exactly who that is who teaches that subject. We'll be potentially here in the coaching session again, and maybe hopefully you can help answer that question then.
Okay, got it. No, but I think what you showed is clear, and I think the concept of atomicity is, I think is useful, and especially using a queue with a circular buffer as a circular buffer. So that's certainly
And I mentioned before that you could still use atomics with a linked list as well. And I guess the only thing I want to say on that front is that atomics don't have to be to update integers. Well, sorry, numbers. Atomics, in this case, we have like a read pointer and a write pointer. The atomic is essentially incrementing that as a number, if you will. But you can also use atomics to update the next pointer in a linked list. So if you have a linked list and you want to add something to the end of the list, what it really is a question of is who or which thread is able to update the next pointer at the end of the list first. So you can make that next pointer update also an atomic operation. And then furthermore, the ability to do an atomic operation is probably limited in terms of the number of bits that your system is. Like on a 64-bit system, your atomic operations can probably be in 64-bit increments. But if you have something like a circular buffer with read and write pointers, your circular buffer likely isn't going to be gigabytes in size. So you probably only need actually a 32-bit or a 16-bit integer to adequately represent the read and write pointers. So if you have a 64-bit system and you only need 16 bits to represent the write pointer, that potentially means you have 56, 48 more bytes to store some other useful data in. So if you, normally the downside to atomics is you can only update one thing atomically. And if you have two pieces of state you need to update, it becomes difficult to get them both updated atomically at the same time. But if you're able to create some sort of structure, some sort of data structure, where you have multiple fields in that structure that add up to 64 bits in total, or 32 bits on a 32-bit system, you can then take advantage of atomics to write atomically multiple logical pieces of information at once. And I think that's something that people oftentimes forget, is that you're not stuck with atomics that way. But once again, atomics are tricky, and unless you're like feeling confident about them, or I guess unless you have to, I would consider whether or not that's how you'd want to implement the solution if there's not a requirement for it to be optimized in a way that atomics would allow you to optimize it.
Well, I think here we are using the atomicity to kind of make the operation thread safe. So we would have to use that or use another thread safe method.
Yeah, no, I mean, once again, anything that you do in atomics, you could do it with locks. Kind of by definition, any implementation you have that uses atomics, you could have an almost identical implementation that just adds a lock before and after that load or store operation. Just the problem with there's usually downsides to mutexes or using mutexes, and usually the efficiency of your solution is going to be lower. It doesn't, not always, but oftentimes is going to be lower with a mutex-based implementation. Cool. So if there aren't any other questions or topics, maybe I will, let's see here. I have a bunch of topics that I have talked about in the past, and I honestly don't remember if people here have been there. I don't want to just repeat something that you guys are already comfortable with.